Okay, I'm going to go through the studying pedigree activity with you now. So a pedigree is just a visual chart, a way of following a family history of a specific trait. So this is a pedigree. It's a visual chart that depicts a family history or the transmission of a specific trait. They can be interesting to view and can be important tools to determine the pattern of inheritance of specific traits. Pedigrees are used primarily by genetic counselors, which is an interesting career to look into, when helping couples decide to have children when there is evidence of genetically inherited disorders in one or both families. They are also used when trying to determine the predisposition of someone to carry a hereditary disease. For example, familial breast cancer. So that's breast cancer. There's a gene for it, and sometimes that gene can be passed through a family, and then you'll end up with several family members that have breast cancer or related cancers there. So they can use a pedigree to trace that. Okay, some things to know about pedigrees. Circles. Circles are going to represent girls, females. And I remember girls are usually more curvy than boys, so circles are females. Squares are the males. Okay. If a shape is shaded in, like these right here, these are shaded. That means they are showing that trait. Their phenotype is for that trait that's being followed by a pedigree. If they are not shaded in, they are not showing that trait. Okay. And there are sometimes circumstances where they may actually be carrying the trait. They may be heterozygous, also known hybrid, heterozygous or hybrid, which would be big letter, little letter. Maybe it's a recessive trait, so they're not showing it even though they're carrying it. Or they could be homozygous for that dominant, big letter, big letter. If it's a recessive trait they're following, for that trait to show up, that person would have to be little letter, little letter. So their genotype would be homozygous recessive for it to show. Again, this is just going back over that. Squares indicate males, circles are females. Individuals that are affected are going to be shaded. Okay. A line between a male and a female. Okay. Male and a female. That line right there represents a marriage. So up here, this female was married to this male. And then this was an offspring that married this person. Okay, this is an offspring that married this person. So the lines going this way indicate marriage. The lines going down and then across these show the offspring. So it comes out of this marriage. We have that son, that daughter, and that daughter. Okay, this is not an offspring of these parents. This person married in. This is a son-in-law married to this daughter, and then this would be their children. Okay. And again, right here it shows sometimes it'll be half shaded. That would be a carrier. That would mean that we were looking at a recessive trait. So this would be big letter, little letter. They're carrying that gene, but it's not showing up phenotypically. So a pedigree is just like a family tree, except that it focuses on a specific genetic trait. A pedigree usually only shows the phenotype for each family member. It doesn't show the genotype. It usually just shows the physical characteristic, that phenotype. And then we can figure out what the genotype is based on those phenotypes. Okay, with little thought or hints below, we can figure those out. So hints. If an individual is homozygous recessive, then both parents must have at least one recessive allele. Okay, if they're homozygous recessive, we'll just say little n. That means mom had to have a little n to give them, and dad had to have a little n to give them. So both parents would have at least one little n. And then based on whether or not they're showing the trait, then we could figure out what their other gene would be. Okay. If an individual shows a dominant trait, then at least one parent must have the dominant phenotype. Okay. So if you have an offspring, if we're looking at dominant traits, if we have an offspring with that dominant trait, then at least one parent had to have that dominant trait. If both parents are homozygous recessive, then all of the offspring will be homozygous recessive because they can only give those little letters. Okay. So that note right there says, in a pedigree, the trait of interest can be dominant or recessive. The majority of harmful genetic conditions are only seen when an individual is homozygous recessive. The most of the time, if it's dangerous, it's only going to show up in the homozygous recessive trait. There are a few exceptions. Examples of conditions caused by recessive alleles include cystic fibrosis, a disease of secretory glands, including those that make up mucus and sweat. Fanconi anemia, which is a blood disorder. Albinism, which is a lack of pigmentation. And phenylketonuria, which is a metabolic disorder. Some genetic conditions are caused by dominant alleles and may therefore be expressed in the homozygous dominant or the heterozygous individuals. An example of conditions by dominant allele include polydactyly, which is the presence of extra fingers, achondroplasia, which is a type of dwarfism, neurofibromatosis, which is a nervous disorder, and there's a disease known as familial hypercholesterolemia, which affects individuals suffering from heart disease due to abnormally high cholesterol levels. Okay. So we're going to look at this pedigree right here and see what we can figure out. Okay, this is a pedigree right here, and it's a recessive trait. So we're going to see if we can figure out the genotypes based on these phenotypes here. So it says, wants to know a male. So this person right here, we know if it's showing it, if it's a recessive trait, it's going to be a little letter. Okay. So let's answer these questions right here. We want to know who is a male. So a male. We said females are circles, males are squares. So if it's a male, then it's going to be C. Female, that's going to be A. A marriage, we said a marriage is the line that links the male to the female. So that would be a marriage line there, so that is B. Right there. And then it says a person who expresses the trait. Well, we said if they express the trait, they're going to be shaded in. So out of those, A is shaded. A is expressing that trait. A person that does not express the trait, the one that are labeled that doesn't express the trait would be C. A connection between parent and offspring. So parent and offspring. Okay. This was the marriage between the parents, and then out of that marriage comes these offspring. So D is the line that goes down and then across to the siblings. So D would be the offspring. Right there. So how many generations are shown in this chart? We have 1, 2, 3 parents, their children, and then their grandchildren. And a lot of times you'll see those labeled as generation 1 with a Roman numeral. And then generation 2 and generation 3. A lot of times you'll see them labeled like that. And then these might be 1, 2, 3, 4, 5, 6, 7. And then you might say generation or person 2, 1. That would be generation 2, person 1 would be the daughter. 2, generation 2, person number 2 would be a son-in-law married in, and then that's how that would work. So that's 3 generations. Oops, this should be 3. Generation 1, generation 2, and generation 3. So there are 3 generations. So assuming the chart above is tracing a dominant trait, because it's tracing a dominant trait called white forelock through the family. F is a tuft of white hair on the forehead. Okay? So it's a dominant trait, so we know that if it's a dominant trait and it's showing up, this person right here has at least one big F for the forelock. This person is not showing the trait, so they have to be little f, little f. Okay? Then we come down here and we look at their offspring. So this daughter right here is showing the trait. So she has to have at least one big F because they said it was dominant. And Dad could only give a little f, so she has to be big F, little f. That looks more like a big F than a little f, doesn't it? She would have to be big F, little f. Because She's showing the trait, so she got a big F from mom. But Dad was not showing the trait. Dad was recessive, so he could only give her a little F. So she has big F, little F. Okay. We're not going to worry about him yet because he was not an offspring. This person is not showing the trait. It's the daughter of those two. So this person would have to be little f, because it's not showing the trait. It was a dominant trait, so it has to have just recessive alleles. This person is showing the trait, so they got the big F from mom. And Dad can only give a little f, so this person has to be big F, little f. And this child is not showing the trait. Let's make it look kind of hard there. This is not showing the trait, so he has to be little f, little f. Okay. He's married to someone who is not showing the trait, so we can go ahead and fill this person in. This person is little f, little f. And of course, Dad can only give a little f, Mom's can only give a little f. So little f from Mom, little f from Dad, little f from Mom, and little f from Dad. Those children had to be little f, little f's. Okay. So, go back over here. This son was little f, big F, little f, because it got the big F from Mom. And I'm going to make that where we can tell what it is a little better. This was big F, little f. This one is not showing the trait, so this one has to be little f, little f. This one's not showing the trait, so this one's little f, little f. This one, showing the trait, had to get a big F from Dad. This one had to get a big F from Dad. Mom only had little f's to give, so we know these have to be big F, little f. And then over here, this daughter was big F from Mom. Dad can only give a little f, so we know she had to be big F, little f. This person doesn't have the trait, so this person has to be little f, little f. These have to be little f, little f. And this one has the trait, so it has big F from Mom, and Dad can only give a little f. That would be our alleles for this. Not too bad, was it? And so it says, what is the most likely genotype of individual A? So individual A, well, individual A, we know we had offspring who had big F's, and we had offspring that were little f, little f. So we know Dad gave a little f, and if this offspring is little f, this is what we would call a test cross. If this offspring is little f, that means Dad gave a little f, but Mom also had to give a little f. We know Mom had the trait, so she had a big F. Now she has a, she has a little f because this one got a little f from Mom and Dad, and this one got a little f from Mom and Dad. So little f from Dad, but then another one had to come from Mom. So Mom had to be big F, little f. Big F, little f. So what is the most likely genotype of individual C? Individual C was Dad not showing a trait. It was a dominant trait, and he's not showing it, then he's little f, little f. And that's that. Okay. Flip over and we'll do that next page. Okay, so Fanconi's anemia. Form of the trait. The dominant form is normal bone marrow. So normal bone marrow is the dominant form. Recessive is having the Fanconi anemia. So if someone's showing the trait, they're showing that recessive trait, then we know they're going to have to be little letter, little letter. Okay? If it's a recessive trait and it's showing up, they have to be little letter, little letter. So we can go ahead and fill those in. We know that Arlene is showing the trait here, so she has to be little f, little f. For Fanconi's anemia. Wilma is showing the trait, so Wilma has to be little f and little f. Tom is showing the trait, so Tom has to be little f, little f. Okay. Well, George is not showing the trait, so we know he has at least one dominant allele, so he has a big F. And then we can look at their offspring. Notice Mom's little f, so she could only give little f's. Dad has at least one big F. Okay, but if we go back and look at Tom and Wilma, they have the trait. They have two little f's. So one gene has to come from Mom, one gene has to come from Dad. Okay, So if Mom gave a little F, Tom has two little F's. The other little F would have had to have come from George. So we know he had a big F because he doesn't show the trait. He's showing the dominant phenotype. And then we know he also has a little F because he had to give a little F to Tom and he had to give a little F to Wilma. Okay. It shows us that Sam is big F, little F. He got big F from George and he got the little F from Arlene. Anne is showing the dominant phenotype, so she has a dominant allele. She got big F from Dad. Dad's big F came to her. But Mom only had little f, so we know she is also heterozygous. She is big F, little f. They're showing the dominant phenotype of normal bone marrow. Okay. Then Michael, Anne married Michael. And that's their marriage there. Anne married Michael. Michael does not have the trait, so we know that he does have a big F. He's showing the dominant normal bone marrow. But then they had Carla. Carla does have the anemia. She has two little F's, so that F came from Mom, and then one F would have, little F would have had to come from Dad. So Dad has to be big F, little f. Okay. Then we'll come over here and let's look at Sandra and Tom's marriage. Okay. So Tom has a little f, and we know that Sandra does not have the trait, so Sandra has at least one big F. She has a big F. Daniel is her offspring, big F from Mom, and a little F from Dad. Alan is her offspring. He's not showing the trait either. So we know he has a big F from Mom, because she's the only one that had a big F. Dad had two little F's, so he had to get a little F from Dad. Okay. And Alan married Tina. Tina is not showing the trait, so we know that Tina has at least one big F. But she could be big F, or she could be big F, little f. We're not sure. And then they had Christopher, who also does not show, but he could have gotten that little F from Alan, or he could have gotten a little F from Tina. I mean, a big F from Tina. And he could be big F, little f. We don't know. So we cannot know for sure what this second one is for Tina. And same thing over here for Sandra. Okay. We don't know necessarily what that one is either. Okay, so let's look at the questions real quick. What is Arlene's genotype? Well, back up here at Arlene. Arlene has a trait. It's a recessive trait, so she is little f, little f. George's genotype. George did not have the trait, but he had children who did, so he had to be big F, little f. That's little f. Anne and Michael's genotypes. Well, Anne and Michael, neither one of them had the trait, so they both had a big F, but then they had a child who had two little F's. So one little F from Anne and one little F from Michael. So both of them had to be big F, little f. Okay. Most likely, Sandra's genotype is, well, we're not sure. You could go either way for Sandra. Okay, so she is big F. We know she has a big F, but she could be homozygous big F, or she could be heterozygous big F, little f. With only two children, is a little iffy. If they had like 10 children and they all had the big F from Sandra and nobody had the trait, then we would be pretty sure that she was homozygous big F. Or if they had a couple more children, if maybe their next child ended up having the trait, then we would know that that child was little f, so Sandra would have to be big F, little f. With just the two children and them both having a dominant trait, then we don't know for sure. Okay. So 3 people on the chart, other than George, who most likely are carriers. Well, carriers are the heterozygous, the hybrids. So Michael would be a carrier, Anne would be a carrier, Sam's a carrier, and Sandra, we don't know for sure. Flip over one more page. Okay, neurofibromatosis. Okay, neurofibromatosis is dominant. The dominant form is having neurofibromatosis. The recessive form is not having it. So if the trait shows up, then we know they have at least one big N. Okay, so that one has at least one big N. If the trait does not show up, then it has to be little n, little n. So Dad here has to be little n, because he does not have the trait. Okay, so let's look at their offspring. Okay, this daughter does not have the trait, so she's big N. I'm sorry, she's little n. It's a recessive. Normal is recessive, so she would have to be little n. She does not have the trait. She's normal, little n. This daughter does have the trait, so we know that she got a big N from mom, and then dad only had little n's to give, so she has to be big N, little n. When she's showing the trait's dominant, so she got that dominant allele from mom. And then dad only had little this. Okay, mom, we can go back and look at mom right here now. Okay, this daughter has a recessive phenotype of being normal, so she has to be little n, little n. Well, dad gave one little n, and we knew that mom had a big N because she's showing the trait. We weren't sure about that, but if we look at this daughter, she had to get a little n from mom. So we now know that mom was big N, little n. Mom's big N, little n. She gave this daughter a little n. She gave this daughter a big N. Okay, this son does not have it. He's little n, little n. This son does have it, so he had to get that big N from mom, and then dad would have to give a little n. So this daughter also had it, got the big N from mom, little n from dad, and she married someone who was phenotypically neurofibromatosis. So we know that this parent that married N, person number 2 here, has at least one big N. So we can go back and look at their offspring then. This offspring does not have the trait, and it's a recessive trait, so we know this offspring is little n, little n. So that little n came from mom, and then dad also had to give a little n. So we now know that dad is big N, little n. Okay. And then we can't know for sure that one. It may have gotten the big N from mom and then could have gotten a little n from dad or a big N from dad. And same thing with this one. May have gotten a big N from mom and a little n from dad, or may have gotten a big N from mom and a big N from dad, or vice versa. So we can't know for sure. This one is not showing the trait, so we know it has to be little n, little n. Then we go back and look at this one over here. This daughter who was not affected, had the recessive phenotype of no neurofibromatosis, married somebody else that was little n, little n. So of course mom can only give little n's, dad can only give little n's. Mom can only give little n's, dad can only give little n's. So all their offspring would be little n, little n. So as individual number 1, most likely homozygous, dominant, or heterozygous? Well, we figured out that individual 1 had to be heterozygous because here, just looking at these two, dad only gave little n's, so all these little n's came from dad. And here, mom had to give a big N to this individual, and then this individual had got 2 little n's, so one came from mom and one came from dad. So we know that individual 1 has to be big N, little n, because it has offspring that are heterozygous and offspring that are homozygous recessive. Okay. And what's the genotype of individual 3? Okay, individual 3 is right over here. It is a recessive, normal is recessive. It's showing the normal recessive trait. To show the recessive trait, it has to be little n, little n. So individual 3, number 2 there. Individual 3 would have to be little n, because it's showing the recessive trait of not having neurofibromatosis. And then number 3 says, can you be sure the genotype of the affective siblings of individual 3? No, we can't, because both parents are heterozygous, which means it could have given a big letter and this one given a little letter, or this one could have given the big letter and this one a little letter, or could have given a big letter and a big letter. We don't know. We just know that they have at least one big letter. Can't know for sure. And that's it for Pedigrees. Hope that helps.